Welcome back. So this is lecture 31 in this course on Bayesian modeling. The topic of today's lecture is MCMC sampling. Okay, so we are going to discuss a particular sampler based on Markov chain Monte Carlo. So actually this method Markov chain Monte Carlo has multiple versions. You can implement it in different ways. So there are multiple samplers that you will see based on this particular method, right? One of such sampler is Metropolis Hastings sampler. You can also call it Metropolis Hastings algorithm based on Markov chain Monte Carlo. Okay. So in this lecture particularly, we will take a look at how does this Metropolis Hastings sampler work. Okay. So it is based on idea of Markov chain Monte Carlo, but we will work out each step. So how do we implement it in each step, right? So let us begin. So just to summarize, what is the basic idea behind Markov chain Monte Carlo? The idea was this, that we were replacing independent sampling for proposal generation by a dependent sampling. Okay. So rather than drawing a sample from an independent density like Q of theta, we will draw a sample from a proposal density conditional on current state of the chain. That means the proposal or the sample that you have already collected from the posterior, because you are continuously collecting these samples from the posterior distribution, right? So we will generate a next proposal based on a sample that you have already collected from the posterior. So this is a posterior sample that you have just previously sampled. Okay. So that's how we do proposal generation. So that's why each time our proposal is conditional on current state of the chain. So basically the sample that you have already collected, right? So each new sample is going to be dependent on just its immediate previous sample, right? So that's how it follows a Markov process. Okay. So just to describe, let's say this is your true posterior density P of theta given x, right, for some parameter theta, and let's say there is a sample that you've already collected theta I. Okay. Now conditional on theta I, you would generate a new proposal. So in step 1 of the algorithm, you would generate a new proposal conditional on current state of the chain. So for example, you can generate theta star using a normal distribution with mean theta I and some standard deviation sigma. Okay. So basically what we are doing, we are adding some random noise to the current state of the chain so that it generates a new proposal which is close to theta I, but it could be in either direction. So we are generating a new proposal close to the current state, but it could be anywhere in this region, for example on this side or on this side. Okay. So suppose the next proposal you generate is somewhere here. So let's say your theta star is here. So if you calculate now the posterior density of theta star, and posterior density of current state of the chain theta I, okay, which one is higher? Of course the posterior density of theta star is higher. So that's why if this is the case, then you would accept this new proposal theta star as, so this is step 2 where you are evaluating the proposal. Okay. So if this ratio is greater than 1, so basically posterior density of theta star is greater than current state of the chain, then you would accept theta star as new sample from the posterior. So basically in your Markov chain, theta I plus 1 becomes equal to theta star. So basically you update the chain. So the new placeholder in the chain gets this proposal theta star, right? And you begin this process by initializing a Markov chain. So you start with an empty Markov chain. You initialize this Markov chain with some value of the parameter, let's say theta 1. Then conditional on this, let's say using a normal distribution or some density q of theta given theta 1, you generate a new proposal theta star. Now you compare posterior density of theta star and theta 1. If posterior density of theta star is greater than theta 1, then you accept theta star as a new sample theta 2, or you reject it, right? So there are criteria for accepting and rejecting it that we will discuss, right? But that's the basic idea. Then once you have collected theta 2, then you generate another proposal theta star, and you will accept theta star if its posterior density is higher than theta 2, or let's say probabilistically if its posterior density is lower than theta 2. So that will become theta 3 if you accept it. If you don't accept it, then you again draw a proposal based on theta 2. Okay. So that keeps on going until you have collected, let's say, n number of samples. Okay. So this is the idea behind Markov chain Monte Carlo. Now we'll take a look at this particular sampler, Metropolis Hastings sampler, and we will see the steps of this algorithm. How does this algorithm work? Okay. So Metropolis Hastings algorithm. So this is a version of Markov chain Monte Carlo. So the basic idea remains the same. It's just that exactly what kind of proposal density we will use, exactly what will be our formula of evaluating a proposal, and what would be your decision criteria, that can change slightly, right? So step 1. So in this algorithm, step 1 that you need to do is this, that initialize a Markov chain. Okay. So you will begin with an empty Markov chain, right? And you initialize this Markov chain with a value of parameter, and you can sample this value parameter, let's say from its prior density, or you can just randomly put a value, let's say 0, 1 or anything. Okay, so it should be a reasonable value though. So let's say you sample it from its prior density. Okay, so that will work fine. So this is step 1. In step 2, now step 2 will have iterations, right? And in each iteration, okay, these are the steps that you will take, right? So step 2.1 is generate a new proposal conditional on current state of the chain. How we do this? So let's say generate a new proposal theta star from a density q of theta given current state of the chain, let's say theta I. So that's how you generate a new proposal. Okay. Once you have a new proposal, then you would evaluate it. One thing that will happen in generating new proposal is this, that along with current state of the chain, this thing would have another parameter, sigma. Okay. What this parameter does, it determines that how far you can generate a new proposal from the current state of the chain. For example, you have seen this particular density. So let's say I say that my proposal density is a normal density with mean theta I and standard deviation sigma. Okay. So what would sigma do here? So why sigma matters here? Okay. Let's say the current state of the chain says that theta I is equals to 0.4 and your sigma is, let's say, 5. What would it imply? What it would do is something like this. So let's say this is your true posterior distribution and your theta I is here, let's say 0.4. This is your theta I. Okay. If you generate from this particular density with mean 0.4 current state of the chain but standard deviation of 5, it can generate new proposal theta star anywhere in this region, basically in this huge range around this current state of the chain. So let's say new proposal it generates, it's somewhere here. Let's say here you get theta star. and then based on this new proposal you generate is somewhere here. Okay. So if you keep on generating from this particular proposal density, then it becomes like another independent distribution. Then this distribution, then this proposal density is not generating dependent proposals anymore. And when does this happen? When your standard deviation is too large. Okay, so when a standard deviation is too large, then you are randomly drawing sample in this parameter space, right? Then actually you are not making any use of information that you already have. What information do you already have? That this current state of the chain, the sample that you have, theta equals to 0.4, it exists in a relatively good posterior density region. So let's say theta exists somewhere here. Okay. If you do not generate a proposal close to theta I and you generate a proposal somewhere, let's say here, okay, then you are not making any use of this information that 0.4 already is in a non-zero posterior density region. Okay, you are wasting that entire benefit of using a MCMC algorithm. Okay, so it is very important that the value of this parameter sigma is not too large, because if it is too large, then you are doing independent sampling and you will also end up rejecting a huge number of samples. I will show you why. Okay, you also will end up rejecting a huge lot of samples. So does that mean that sigma should be very small? Well, that is also not true. If sigma is very small, then that also creates a huge number of problems. We will see what kind of problems it can cause. Okay, but for now let us understand that it is very important to have a reasonable value of this parameter sigma. Okay, so so whatever proposal density you would choose, it would have some kind of parameter sigma, which is basically indicating the amount of noise you are adding to the current state of the chain to get the new proposal. So you are adding this much perturbation to the current state of the chain to get a new proposal. Okay, but how much perturbation, how much noise do you add? Okay, that matters. Okay, we actually call it the step size parameter. In this Metropolis Hastings algorithm, we call the sigma a step size parameter. This is a version of random walk algorithms. What we say in random walk algorithms is that if you are currently at theta equals to 0.4, okay, so let's say if you are currently at theta equals to 0.4, okay, and you are generating a new proposal, you are basically walking on this flat space. See this x-axis space, you are walking on this flat space, right? So when you generate from this density, you will take a step either in this direction or this direction. Basically, you are walking on this flat space and you will take a step in either direction from your current state, from your current position, right? How large a step you can take, how big a step you can take from your current position is determined by this parameter sigma. So if sigma is too large, you can take a huge step in either direction. If sigma is small, you will take a very small step from your current position, right? That's why it's called a step size parameter. Okay, and this is a very critical hyperparameter for the efficiency and posterior recovery for this particular algorithm, because you have seen that if sigma is too large, the algorithm becomes like an importance sampling algorithm where you draw samples from an independent density. If sigma is too small, then that can create another kind of problems. Posterior recovery would be really bad. I will explain why. Okay, so that's why it is very important that we choose a reasonable step size value, right? So once you have generated a new proposal conditional on current state of the chain and some step size parameter sigma, okay, then in step 2 we evaluate the proposal. Or how do we evaluate the proposal in this case? We calculate Hastings ratio. What is Hastings ratio? Hastings ratio is actually posterior density of this proposal theta star given the data divided by posterior density of previous sample that you have collected, theta I, basically current state of the chain given the data. Okay, so the ratio of their posterior densities. What will be posterior density of theta star? So it would be likelihood of theta star given the data, prior density of theta star divided by marginal likelihood. So let me just write only posterior density of theta star. Okay, so it would be likelihood prior density of theta star divided by marginal likelihood, which is basically likelihood into prior with respect to theta. Okay, also you need to take care of the bias that we are already generating this proposal theta star from this density q of theta. So, I need to divide it by probability density of generating theta star given theta I. Okay. So, this will give you posterior density of theta star. Similarly, what would be posterior density of theta I? So, it would be likelihood of theta I, prior density of theta I divided by likelihood of theta I, prior density of theta I, d theta, or not theta I, just theta, right? Theta I is just a particular parameter value. Okay, you can write it like this: prior density of theta into d theta. Now this whole thing divided by proposal density of theta I. So what is the sampling distribution of theta I? So we do not want it to depend on other previous samples. So we just want a relationship between theta star and theta I. So you can write, let's say, backward density of proposing backward, we call it backward transition kernel. So backward transition of theta I given theta star. Okay. So if we take a ratio of these two, ratio of posterior density of theta star and posterior density of theta I, we get our Hastings ratio. So what happens when I take this ratio? When I divide this thing by this thing, this marginal likelihood term will cancel out, because this is something will remain the same regardless of whether your parameter value is theta star or theta I, does not matter, right? Because marginal likelihood of this model would remain a constant. So this will cancel out when we take the ratio. So only thing that remains in your Hastings ratio is this likelihood of theta star given the data, prior density of theta star divided by likelihood of theta I, prior density of theta I, and then here you have this forward transition, proposal density of theta star given theta I, and here proposal density of theta I given theta star. If your proposal density is symmetric, so let's say you are drawing theta star from a normal distribution with mean theta I and standard deviation sigma, in that case this density and this density would be equal if it is a normal distribution. So basically the probability density of observing this given this as mean will be equal to probability density of theta I given theta star is the mean. Okay, so basically both these densities will be same. So if I write it in form of d norm, so you can check this. Let's say d norm of observing some value, let's say 0.6, given the mean is 0.4 and standard deviation is 1, will be same as d norm of observing 0.4 when the mean is 0.6 and standard deviation is 1. Okay. So this is because this distribution is symmetric. So these densities remain the same. So this will cancel out if the proposal density is symmetric. If not, then you can keep it. Okay. So this is Hastings ratio. So what this ratio is doing, it is calculating the actual ratio of posterior densities of the current proposal, of the proposal that you have generated, and the current state of the chain based on the sample that you have already collected, right? So if h is greater than 1, what would it mean? If h is greater than 1, that means theta star has higher posterior density compared to theta I. That's what it means. And if theta star is higher posterior density, we should accept it. So in that scenario, we should accept theta star. So that is the role of h. Now we will see how we use h in the next step of the algorithm in 2.3 step, right? So accept or reject the proposal. So how do we decide whether we accept or reject the proposal? What you can do is this, that let's say we generate value of a variable z from a Bernoulli distribution, okay, with parameter, let's say p, okay, where p is equals to minimum of 1 and h, okay. So we generate z from the Bernoulli distribution with parameter p, where p is equals to minimum of 1 and h. So if z is equals to 1, then accept theta star. So if z equals to 1, accept theta. What does that mean? That if you have a Markov chain, then in the Markov chain, theta I plus 1 becomes equals to theta star, okay. And you update the current state of the chain as well, right? So that becomes I plus 1 becomes the current state of the chain. You can write it here, update current state. Else, if z equals to 0, what you will do now? You reject theta star. You can also count how many samples you have rejected, all those things. Importantly, what you will do is this, that do not update the current state of the chain. And in both these cases, you will go back to the same thing. So basically, you go back, repeat steps 2.1 to 2.3. Okay. So that's the algorithm. So just to briefly summarize again, we start with a proposal generation. We generate a proposal from proposal density q of theta, given current state of the chain theta I, and also in step size parameter sigma. And the step size parameter is important. It determines how much noise you're adding to the current state of the chain. And then once you have generated the proposal, you evaluate this proposal using Hastings ratio. So the formula of Hastings ratio is given by this. So it is likelihood into prior for theta star, forward density multiplied with backward density kernel q of theta I given theta star divided by likelihood of theta I, prior density of theta I, theta is current state of the chain, and forward transition q of theta star given theta I. So this is Hastings ratio. Now from Hastings ratio you will calculate this p. P is probability of accepting the proposal. Okay, so how does it work? So suppose h is equals to 1.5. If h is greater than 1, h equals to 1.5, then the value of p will be 1 because you are taking minimum of 1 and h. Okay, so in that case minimum is 1. So if h is greater than 1, probability of accepting the proposal is 1. If h is less than 1, then the probability of accepting the proposal is h, right? So we accept the proposal with probability h. So we generate our decision criteria from a Bernoulli distribution. So if p is 1, this will always generate 1. If p is less than 1, it would sometimes generate 1. So if it generates 1, if our decision criteria is satisfied, then we accept theta star as new sample for the posterior, and we update the current state of the chain. Okay, so this is how a Metropolis Hastings algorithm work. Now let me explain the importance of step size parameter. What happens is this: let's suppose this is your actual true posterior distribution. Okay, so P of theta given x, here you have theta, and let's say this is the current state of the chain theta I. Okay, suppose your step size sigma is too small. If your step size is too small, let's see what would happen. What would happen is this, that you would generate a new proposal, let's say theta star, which is very close to your current proposal theta star. Okay, so you have generated a new proposal theta star. Okay. Now should we accept theta star or not? So h will say that h will be greater than 1, so we will accept theta star. Okay, now let's say I again generate a new proposal. It would be again very close to theta star. That's a new proposal, theta star is here. So I should again accept theta star, right? Now I again generate a new proposal which will be here. The new proposal would be here. So I will keep accepting some of them and keep rejecting some of them. But if my step size is too small, then what would happen is this, that if I decide that I am going to collect total 4,000 samples from the posterior, you start with an empty Markov chain, right? So let's say I start with empty Markov chain containing 4,000 empty slots, which is basically I've decided that I will collect 4,000 samples from the posterior. What can happen is this, that you will collect all those 4,000 samples only from this region. If your sample size is too small, you will be able to explore only a very small part of parameter space. You won't be able to explore this whole space in this direction. Why? Because your step size is too small. You are generating new proposals only within this region. You haven't reached anywhere close to this particular region. Okay, you never explored this region. Basically, you got stuck in this particular region of the posterior. So you are drawing a huge number of samples only from this part, and you couldn't explore the whole parameter space. We technically, basically we call this that chains are getting stuck. So your Markov chain is getting stuck in this particular region of the posterior. It is not able to explore the whole parameter space. And it will depend on where you initialize your Markov chain. So let's suppose you initialize your Markov chain here. Then if a step size is too small, your sampler can get stuck only in this region. Okay. Why? Because step size was too small, that whatever new proposals you generated, they could never cross these boundaries or whatever certain boundary. So new proposals you are generating were so close to the current state that you are moving too slow. So even though you are doing the same process, you are accepting and rejecting samples, all that is fine, but you are moving too slow. Okay. So if step size is too small, your chains will move slowly. You might get stuck in one part of the posterior. You may not be able to explore the whole parameter space. As a result, what you get is highly correlated samples. That means you get samples only from a small part of the posterior distribution. You are not able to explore whole parameter space. Okay. And in this case, you will see, as we will visually inspect these Markov chains look very different. And in fact, if you have multiple Markov chains, they will explore different parts of posterior. Okay, so this is even more dangerous than having a large step size. With large step size, you have the problem of computational efficiency, because as step size increases or becomes larger and larger, you are doing almost independent sampling. You are running here and there in the whole parameter space, right? So your sampling becomes very slow. You end up rejecting a huge number of samples. You are not making a good use of the information contained in your previous samples. But if your step size is too small, then you will end up getting an incorrect posterior. You won't be able to recover the posterior distribution because you won't be able to explore the whole parameter space. So you might get stuck in one part of the posterior or in one part of parameter space. Okay, so that's the danger of having a very small step size. Okay, so this was an introduction to Metropolis Hastings algorithm. Okay, so just to summarize, this is one of the version of this is one particular sampler under this approach of Markov chain Monte Carlo. And the basic idea in Markov chain Monte Carlo, as you know, is that we generate a new proposal based on current state of the chain. So basically generate a new proposal close to the current state of the chain. Because we know the current state of the chain is from relatively higher posterior density region. So we want to generate new proposals close to that, right? So we are using information contained in the existing samples. Once we have generated proposals, we evaluate the proposal using Hastings ratio, okay, where we take ratio of posterior density of our new proposal and posterior density of current state of the chain. If this ratio is greater than 1, then we accept theta star. So we take this decision using this criteria. We calculate a probability of acceptance, which is minimum of 1 in H. So if H is greater than 1, this probability of acceptance is always 1. If H is less than 1, then probability of acceptance is H. Based on this probability of acceptance, we generate decision criteria from a Bernoulli distribution. And based on this decision criteria, we either accept theta star or we reject theta star, and then update the current state accordingly. And we repeat these steps 2.1 to 2.3. Basically, these steps of proposal generation, evaluation, and acceptance and rejection until we have collected n number of samples, let's say 4,000 samples from the posterior. Okay, until then we do repeat these steps. All right, so I will stop here. In the next lecture, we will see how to implement Markov chain Monte Carlo sampler in R. So we will write a code step by step that how do we implement these samplers in R, and we'll take a simple example. All right, thank you very much.